Most people assume a vision language model describes an image by kind of averaging everything it sees. That is the wrong mental model. The surprising part is that a small, identifiable set of attention heads, which are the model's internal spotlight movers, seems to control where the model looks while it talks. Gaze heads is a mechanistic analysis method, meaning it tries to find the exact internal parts that cause a behavior instead of just observing the behavior from the outside. It is like finding the tiny spotlight operator inside a theater crew who decides which part of the stage the narrator focuses on, and then redirecting that spotlight to a different actor on demand. That matters because it turns a vague debugging problem into a concrete control problem. If the model talks about the wrong region of an image, you do not have to guess. You can identify the heads responsible and steer them at inference time, which means while the model is running without retraining. Source: http://arxiv. org/ab/2606. 14703 v1. And here is the key twist. Random heads do not help, and touching every head can wreck generation. The practical win comes from first scoring which heads correlate with the current image region, then intervening only on that small subset. That is the difference between blind tinkering and real control. But the next question is how you find those gaze heads in the first place.
Before you touch the steering code, you need a small stack of basics in place, because this technique sits right at the intersection of language models and vision. You should be comfortable with Python, the language most machine learning code is written in. You should know PyTorch, the deep learning library that lets you build and edit neural nets. You also want basic familiarity with transformers, which are models that use attention to decide what matters in a sequence, and attention itself, which is the mechanism that lets the model focus on specific tokens. On top of that, you need a working sense of vision language models, or VLM, which are models that connect images and text in one system. And it helps to know NumPy, the array library that makes tensor-style math easier to read and debug. The biggest mistake here is to assume any attention head will do the job. It usually will not. The paper's approach starts by finding the gaze heads with a scoring pass, meaning the heads that actually correlate with visual focus, and only then intervenes on that small subset. If you try to mask or redirect every head, you can break generation outright. So the prerequisite is not just coding skill. It is knowing enough to measure before you modify. And that matters because the next step is where we separate useful heads from noise.
Most people jump straight to steering a vision language model and wonder why nothing works. The real first step is simpler. Make the model show its attention, which is the internal weight it gives to different tokens or image regions while it thinks. If you can't see that signal, you can't debug it, monitor it, or control it. Here, we load a vision language model, or VLM, which is a model that reads both images and text. Then we run a forward pass, meaning one normal inference pass with no training, and ask for attention tensors, which are the raw numbers behind those attention patterns. Source: http://arxiv. org/ab/2606. 14703 v1. This matters because the paper's method depends on attention in the language backbone lining up with the region currently being described. So at this stage, we are not changing behavior yet. We are only checking whether the model exposes the right signals to work with. But there is a catch most people miss. Most people look at attention heads like they are a pile of wires. The trick is to stop staring and start scoring. Here, a gaze head is just an attention head, meaning one slice of the model that decides what to focus on. Instead of guessing which heads matter, you measure whether a head tracks the region that should be described next. That is the key move. It turns a fuzzy visual inspection problem into a ranking problem. In the paper, comic strips give a controlled testbed, which means the next region is easy to define and compare against. Source: http://arxiv. org/ab/2606. 14703 v1. In practice, that matters because you do not want to intervene on random heads and hope for the best. You want the few heads that actually correlate with the described region, so your steering is targeted, testable, and cheap. Source: http://arxiv. org/ab/2606. 14703 v1. The code shows the workflow in miniature. Each head has attention over 4 regions for several examples, and each example has a true region label. You run a forward pass, which just means one normal pass through the model, and then you ask, did this head put the most attention on the right region? The argmax call picks the strongest region for each example, and the mean score becomes a simple correlation-like measure. That is not the full paper pipeline, but it captures the idea well. The value is speed. You can rank heads with a small number of forward passes before you touch any intervention. That is much better than masking every head in the model, because changing everything often destroys generation. A common mistake is to jump straight into intervention without first finding the correlated heads. First score, then steer. But there is a catch most people miss. Most people think steering a vision language model means retraining it. But the paper shows a much cheaper trick. Change only the few attention heads that already look at the image region you care about. An attention head is one small pathway inside the model that decides where to pay attention. Once you find the gaze heads, the heads that correlate with visual focus, you can redirect them toward a chosen comic panel instead of letting the model drift. The key result is that intervening on the top 100 gaze heads, which is fewer than 9% of all heads, can steer the model to answer about the chosen panel with high accuracy, while random heads do not. Source: http://arxiv. org/ab/2606. 14703 v1. That matters because it gives you control at inference time, which means no retraining, no fine-tuning, and no new labeled dataset. For product demos, assistive tools, and safety controls, that is a huge win. But there is a catch most people miss. You only get this behavior if you first identify the right heads. The surprising part is not that you can steer a model. It is that you can steer it while it is already talking, and it will keep going in the old direction for just a moment before cleanly switching over. That matters because real users do not stay still. They change their mind, point a different object, or correct the assistant mid-sentence. In this paper, the gaze mechanism behaves less like a one-time classifier and more like a live routing signal, meaning it can redirect the model's focus during generation. Source: http://arxiv. org/ab/2606. 14703 v1. The simple way to think about the code is that each decoding step gets its own target region. Decoding means producing text one token, or one small text piece, at a time. So instead of locking the model on a panel 1 forever, you can update the control signal as the conversation shifts. That is why the example builds a list of target regions and loops over them. On step 0 and 1, the model focuses on panel 1. On step 2 and 3, it moves to panel 3. The key production idea is not the toy string output. It is that the same control surface can follow the user's attention in real time. Source: http://arxiv. org/ab/2606. 14703 v1. The warning here is important. Do not try to steer every attention head and hope for magic. An attention head is one small pattern finding unit inside the model. If you intervene on all of them, you usually break generation. The paper reports that changing all heads destroys the output, while targeting only the small set of correlated gaze heads preserves useful behavior. So the right workflow is to run a small scoring pass first, find the heads that actually track gaze, and then intervene only on that subset. That makes the method practical, because you can prototype steering and debugging at inference time without retraining the model. But there is one more catch people miss when they move from demo to deployment. The real test is not whether your trick works once. It is whether it still works when the picture changes. That matters because a head that looks impressive on comic strips might just be memorizing one visual style, not learning a general gaze mechanism. In the paper, the intervention redirects answers on both comic strips and natural Coco images, which are real-world photos with very different structure. It also shows up across model sizes from 2B to 32B, and across some VLM architectures, where VLM means Vision Language Model, a model that reads images and text together. Source: http://arxiv. org/ab/2606. 14703 v1. That tells you the effect is not just a lucky coincidence in one checkpoint. In production, that difference is huge. It is how you separate a control method you can trust from a brittle artifact that falls apart the moment the data shifts. But there is a catch most people miss. A good workflow is to validate the same heads on a second dataset or a different checkpoint before you touch the full model. That is why the little Python harness here matters. It is a toy example, but the logic is solid. Test a few examples from comics, then a few from Coco, and see whether the redirection still happens. The code prints whether each target was redirected, and that gives you a quick sanity check without training anything. The point is speed. You use a small number of forward passes, meaning plain model runs without weight updates to rank heads first. Source, http://arxiv. org/ab/2606, 14703 v1, that is much safer than randomly masking heads and hoping for the best. A common mistake is to intervene on every attention head, which often destroys generation. Instead, first identify the correlated gaze heads with a scoring pass, then intervene only on that small subset. But there is a catch most people miss when the behavior survives across domains. You have something more valuable than a neat demo. You have evidence that the heads are acting like a real control surface, which means you can use them at inference time, the moment the model makes a prediction, instead of retraining the whole system. That is powerful for debugging and steering, because you can prototype fast and keep the base model intact. But do not assume every VLM family will expose the same headset. Some frozen encoder families do not show a comparable pattern, so you need to verify the mechanism on the specific architecture and checkpoint you care about. Source, http://arxiv. org/ab/2606, 14703 v1. If one dataset works and another fails, that is not a bug to ignore. It is a clue that your heads may be dataset specific rather than truly gaze-like. And the next step is to turn that clue into a reliable ranking test.
Most people expect a vision language model to look everywhere at once. That is the wrong mental model. What matters is that a small, identifiable set of attention heads, which are tiny routing units inside the transformer that decide what information gets emphasized, acts like a control surface for where the model focuses while it describes an image. Think of it like finding the tiny spotlight operator in a theater crew. Once you know who holds the spotlight, you can point the story at a different actor on demand. The non-obvious part is that you do not need to change the whole model. You first do a lightweight scoring pass, using a small number of forward passes to rank the heads that correlate with gaze. A forward pass is one run through the model without training it. Then you intervene only on that small subset. Masking or redirecting those heads can shift which region the model talks about, which is exactly what you want in a newsroom review tool or a support dashboard where a human clicks one object and expects the assistant to explain that object, not the whole scene. Source, http://arxiv. org/ab/2606, 14703 v1. This also explains the common mistake people make. If you randomly poke heads, nothing useful happens, because those heads are not the ones steering visual focus. And if you blast every head at once, you usually break generation entirely. The safe move is to verify the mechanism on the specific model family and checkpoint you are using, because some frozen encoder systems do not show the same head pattern. The practical win is big. Treat gaze heads as an inference time control surface, so you can prototype steering and debugging without retraining the VLM. But there is a catch most people miss.
So the big takeaway is simple. Attention heads can act like a steerable gaze, letting you inspect, score, and redirect what a VLM talks about. Quick question, does the strongest attention head always cause the model's description? No, the best head is the one whose attention most reliably lines up with the described region. Quick question, can you change the target while the model is still generating? Yes, and that gives you continuous control over what it describes next. The big idea here is simple. Some vision language models do not just look at an image, they learn to look where the words are pointing. That is what gaze heads are. They are attention heads, meaning small parts of the model that decide what to focus on, and in this case they line up with the region being described. That matters because it gives you a control point. Instead of asking the model to explain the whole image, you can steer it toward one clicked object, one panel, or one area a reviewer cares about. In a newsroom, that could mean a human clicks a face, a chart, or a logo, and the assistant talks only about that part. In a support dashboard, it can explain the exact screenshot region that needs attention. That makes review faster and the output easier to trust. The key warning is to not grab random heads and expect magic. First, find the correlated gaze heads with a scoring pass, then intervene on that small subset. Source, http://arxiv. org/ab/2606, 14703 v1. The practical lesson is that precision beats brute force. If you try to mask or redirect every head in the model, you do not get better steering, you usually break the language generation itself. The paper reports that changing all heads destroys generation, which is exactly why the targeted approach matters. Source: http://arxiv. org/ab/2606. 14,703 v1. So the workflow is: identify the heads that truly track the clicked region, then modify only those. That is better than a naive all-or-nothing edit, because it preserves the model's ability to speak fluently while changing where it looks. One more caution: do not assume the same headset will appear in every vision language model family. You have to verify the mechanism on the specific architecture and checkpoint you are using, because some frozen encoder families do not show a comparable headset. The real next thing to build is an interactive review